Hi, my name is Rodrigo Albuquerque. I'm assistant professor at the University of São Paulo in Brazil. This course is offered to master and PhD students from the São Carlos Institute of Chemistry. All this material can be found at this homepage here. I'm going to follow this book, Molecular Modeling Principles and Applications from Andrew R. Leach. And these are the three references. They may be very informative. This course is divided into 5 parts. In 2 of them, I will discuss the terms of molecular mechanics. Part 3, I will discuss geometry optimization. In Part 4, I will talk about molecular dynamics. In Part 5, I will show some special topics and also very briefly discuss Monte Carlo. Let's begin Part 3. If we have atomic coordinates, which means bond angles and distance, and if we specify a force field, so that we know expressions to describe each term and the parameters inside each term. We can calculate the total potential energy, and we can do many things like geometry optimization, conformational search, molecular dynamics, and Monte Carlo. Just to cite a few examples. In a conformational search, multiple geometry optimizations are done. In molecular dynamics, we need to make a pre-optimization of the geometry before beginning the simulation. And during the simulation, we'll also calculate this total potential energy in order to calculate the force acting on atoms. In Monte Carlo, we need to make a pre-optimization before beginning to change randomly the coordinates of the atoms. Geometry optimization. This technique is based on finding the best atomic coordinates that minimize the total potential energy. In this case, atomic coordinates are changed while this potential energy term is monitored. For instance, we have here one very bad initial gas. When we withdraw the molecule, we have this initial gas. For instance, this angle here, carbon, oxygen, carbon is very small. And some bond distance like carbon is very big. And we move some atoms in certain directions and we get a better geometry where the potential energy is slightly smaller, which means the system is more stable than previously. And we keep changing the coordinates until we get a final structure where this potential energy term is acceptably low. The methods to optimize geometry include Simplex. Simplex is a very famous method. Then derivative methods. The first derivative methods, which include steepest descent and conjugate gradients. And second, derivative methods like Newton-Raphson. We're going to see all 4 methods here. The first part to make a geometry optimization is to draw a molecule. We can use, for instance, Avogadro. It's a free program. It can be used in Windows, Linux, and Mac. Or you can use any other program you like. Hypercane is a paid program. And there are many other programs to draw molecules. Imagine we see here in this axis the total energy, in our case the potential energy of a system, and as a function of 2 variables, for instance, bond distance and the bond angle. And we see here, when we see from the top, we see a contour plot. Let's imagine now one initial gas, point A. The initial gas has a very high energy. Then we generate 2 other points, B and C, by means of slightly changing variable 1 and 2. If variable 1 and 2 are bond distance and bond angle, we can change slightly, we can increase a bit bond angle and we can decrease a bit bond angle, as well as we can increase the bond distance and decrease bond distance, so that we make 2 other points, as you see, A, B, and C. We make a triangle. Each point is a configuration. For each point, we have the 2 variables, and therefore we can calculate the potential energy, which is showing this axis here. Now, we calculate the V steric, the potential energy, for all 3 points, and we ask who is the largest, who is the worst. So let's suppose we have calculated the potential energy, and this is 95 kilocal, this point is 80 kilocal, and this is 77 kilocal per mole. Now we generate point D. We see that point A has the highest potential energy, so we are going to reflect point A through the line connecting point B and C, which means we will generate a new point, which we are calling point D, by the reflection of this triangle, as we see here. This new triangle, it can, as we see here, can just reflect. We can make a reflection of this triangle, as we see in this example, but we could have done a reflection and a contraction, which means you could have generated a smaller triangle, as shown here. But you could also have generated a larger triangle. This means we reflect and expand the triangle. And there are many different ways of generating a new triangle in order to find this point D, which is located here, shown here. In this case, we have made a simple triangle. And so there are different ways. But then we keep moving the triangle. Now we have points B, C, and D. We calculate the potential energy. Actually, for points B and C, it was already calculated. So we calculate for point D. Since we have variable 1, variable 2, we can calculate the potential energy for point D. And we see which of the 3 has the highest energy. And this point is going to be eliminated. Probably is point B, which has the highest energy. And so this triangle would be reflected here. And then you keep moving this triangle, always eliminating the point with the largest potential energy. As we see here in this animation, we reflect here with a little bit of contraction, and reflect again with expansion, and we stop when the energy is acceptably low. This is a subjective parameter. We can say the energy is very, very low when all 3 points of the triangle, they are very close in energy. They differ in 1%. So we just stop and we assume we have finished this optimization. So here's the first point, initial gas, the molecule, which we have drawn, which has these coordinates, variable 1 and variable 2, and a very high potential energy, and we keep moving the triangle until we get to this point. The simplex method is very useful when we are far away from equilibrium, which means we are in a region where the energy is very high. As soon as we move to a region of very low energy, the simplex is not so precise, so we have to move to first derivative or second derivative methods. It's usual to make first the simplex to decrease a bit the energy, the potential energy of the system, and then we use a more precise method. Let's make this exercise. Use the simplex to optimize the geometry of a water molecule using one initial gas given by these parameters. The distance, bond distance are 1.65, both shown here. L and L one is L1, the other one is L2. The theta, this bond angle, is 135 degrees. So this is your initial gas. And let's use the parameters given here for force constant and equilibrium bond distance and equilibrium bond angle. Assume a harmonic approximation. So we know already how to calculate the potential energy for this water molecule, just using bend and stretching terms. Then we have already one initial point, one initial gas here, and shown by this red point in this plot. And now we need to generate 2 other points. So just build 2 other initial gas by changing angle and distance by about 5%. And then we use any grid on a piece of paper to draw the triangles. So we can make a triangle, we can compute then the potential energy for all 3 points, and then we keep moving the triangle until we cannot decrease the potential energy anymore. This is a good exercise to realize what is the simplex method using a very simple system. As I said, simplex is a very good method for systems far away from equilibrium. As soon as we get closer to the minimum, this method is not so efficient. So derivative methods need to be used. In the case of this derivative minimization method, every atom should move in response to a force. And the force is basically the derivative of the potential energy. If we know the potential energy, we can make a derivative and we can take the minus sign of this derivative. Here we get a vector, and then we can find the force acting on each atom in the system. We can call it a restoring force. This operator is shown here. So this is actually a vector, where this is the x component of this vector, this is the y component of the vector, this is the z component of this vector. And every atom has 3 coordinates, so these 3 coordinates are from the first atom, and we can also make the derivative for the second atom, which means we need to take into account the next 3 coordinates, and so on. So we may have many coordinates here. This vector, the derivative of the potential energy, is a vector pointing to the direction of maximum growth of this potential energy. We don't want to make the potential energy even larger. On the contrary, we want to minimize. That's why we have a minus sign here. This vector points to the maximum growth of the potential energy, is called the gradient. This is a vector. It may have many coordinates depending on how many atoms you have. If you have, for instance, 2 atoms, each atom has 3 coordinates, so the gradient vector would have 6 coordinates: x1, y1, z1, and x2, y2, and z2. The minus signal shows that the force, this restoring force, acts on atoms towards the direction to decrease the potential energy. We see here a very simple example. The x component of the force acting on atom I is given by minus the partial derivative with respect to the x coordinate of atom I of the potential energy, as shown here. Let's see a simple example. We have 2 atoms interacting with each other, and we can use any potential energy term here. And we can calculate this term. It could be, for instance, a bond stretching term, but we calculate the total potential energy. Then we calculate its first derivative, and therefore the force acting on all atoms. When you calculate the derivative of the potential energy, we have the gradient, which points to the direction of the maximum growth of the potential energy. If we think that these 2 atoms, they are separated by a large distance, which may be larger than the reference bond distance. If you separate them even more, the potential energy should increase, and we want to decrease. That's why the force should be contrary to the gradient. Since we already know which direction the atom would move, we can move a bit the atoms in this direction to decrease the potential energy. Now we can see, when you calculate the potential energy, we see that the potential energy now is smaller than previously. And now we make the derivative of the potential energy with respect to the coordinates of atom A to find the force acting on atom A to the right. By the way, the force acting on atom A to the right is equal to minus the force acting on atom B, which would be to the left. We keep repeating steps 1 to 3, until all forces or the difference between potential energies, or even this term here, are acceptably small. This quantity is very important. Here we take the transpose of the gradient vector and multiply by the gradient vector. This is the sum of the squared forces acting on each atom. When we divide by the number of coordinates and we take the square root, we get now the average force acting on each atom. When the average force is very, very small, is acceptably small, we can finish this optimization. This quantity here is a summation over all coordinates of the components of all forces acting on all atoms. This call it root mean square gradient. This quantity is very important in geometry optimization methods. This shows how good was a given optimization. The smaller the RMS gradient, the better was the optimization. Let's make an exercise. Let's try to find the x component of the force acting on atom I, shown here below. The interaction between atom I and J can be considered to be van der Waals, and we can use the Lennon-Jones potential, shown here. We can assume that the distance r is actually larger than the equilibrium distance, which means the van der Waals interaction will bring atoms closer. First, to solve this problem, we need to write the distance r as a function of the coordinates of the atoms. We can use the chain rule to get the derivative, the partial derivative of the potential energy. The derivative of the distance r with respect to the x coordinate of atom I is shown here. You just have to solve this derivative. We can just get the x component of the force acting on atom I. It's shown here. So in principle, since the distance r is larger than the equilibrium distance for the van der Waals interaction, the force will be pointing to the right side. We just need to remember that for any interaction, we have x, y, and z components of the force. So we would have a vector force acting on each atom. The force acting on atom J is equal to minus the force acting on atom I. For many terms of the potential energy, there are analytical expressions for the forces. Otherwise, the derivatives are solved numerically, and this is slower and less accurate. We have electrostatic potential energy and stretching potential energy, and for these two terms, we can calculate the force. There are analytical expressions for the force, shown here. We saw right now how to derive the potential energy, and now we can see the first derivative method. We can just derive once the potential energy, and if we derive 2 times the potential energy, we get, for instance, a Newton-Raphson method. Let's talk about the steepest descent method. This is the first derivative method. Point 1 represents an initial guess where we may have 2 variables. Could be, for instance, bond distance and bond angle here. The first step for the SD method is generating a starting point, point 1, this initial guess, and then one calculates the V steric for this point, and then the force acts on atoms, which means we have to make the derivative with respect to the coordinates, and this is going to give in which direction the atoms should move, and the gradient vector would be going up in order to increase the potential energy, and the restoring force would go down, would go in the other direction. And the direction represented here by this dashed line, we generate few points. So we change a bit the coordinates, in order to have few points along this line. Each one will have a different potential energy. And here are the points A, B, C, and D. And we can calculate, knowing the variable 1 here and variable 2, we can calculate now the potential energy for each point. And we can plot in this 2D plot in points A, B, C, and D. This was step 2. Then we can fit a polynomial curve passing on all points here. As soon as we have this curve, you have see the curve, and now you can find the minimum of this curve, which means we make the first derivative with respect to the coordinates would be 0, and the second derivative would be positive, which means there's a minimum. And this is given by point 2. Now we repeat the steps above, steps 1 and 2, until the root mean square gradient is acceptably low, which means at point 2 we have to calculate the potential energy, and then we can make the derivative of the potential energy to find a gradient, which would be pointing in this direction here. And then we calculate the restoring force, which would point in the other direction, shown here. So again, we have a new force, we have a new direction, and then we repeat again the generation of points and making a polynomial fit and so on. So we keep repeating steps 1 and 2. In this case, the first gradient and the second one, they are orthogonal, as shown here. The conjugate gradient is another method to optimize geometry and is based on the first derivative of the potential energy. Again, we have point 1. There's initial guess. Point 1 represents a configuration where you have variables here, variable 1 and variable 2. And then step 1 is just the same as the previous method. We have initial point, initial guess is point 1, and we are going to find the gradient, which would point in this direction, and then we find the force acting on atom would point in this direction. And then we find in each direction, so here's the force, restoring force, and we show in which direction atoms would be moved. So we have now this red line. In this direction, we generate few points, each one with a different hysterics. So we generate new configurations. Each point represents a different configuration of the system where the variables can be different. Again, we generate points A, B, C, and D, which are shown also here. Each point has its own potential energy. And then we fit a polynomial curve through these points, just as we did with the previous method. And we find the minimum of this curve, which means point 2, shown here. So now point 2 is much closer to the minimum than point 1. So from steps 1 and 2, they are exactly the same as the previous method. The difference now comes in step 3. The next direction to move is not only based on the actual gradient of point 2, but it depends on the previous gradient of point 1 and the gradient of point 2. The next direction is actually a linear combination between the actual gradient at point 2 and the previous gradient at point 1, so that the previous information cannot be lost. We see the new direction is given by the new gradient plus a constant times the previous direction. So the previous direction is basically the direction of the gradient. And this k depends on the two gradients, the actual gradient of point 2 and the previous gradient of point 1. So that this direction, they symbolize the direction of the gradient. The gradient will be a vector point in this direction here, going down, and the restoring force would point up in this direction, shown by the blue dashed line. But actually, when you take into account also the previous gradient, we would correct this direction. We'll not use the blue dashed line, but the red one, with the correct one, shown by this expression. We repeat the steps above until the root mean square gradient is acceptably low, or the minimum is reached. This sometimes happens. For instance, if you have a function of two variables, the conjugate gradients method takes only needs two steps to locate the minimum. In real case, we have a multidimensional surface. We have many variables, and we need many steps to locate a region very close to the minimum. The Newton-Raphson is a second derivative method. It's very efficient close to the minimum. This method is based on this matrix, where each matrix element is a second derivative of the function f. In our case, f is the potential energy, with respect to the coordinates. We have here q1, q1, q2, q1, q3, q1, q4, until q1, qn. This matrix is called the Hessian matrix. It needs to be invertible, and matrix elements must be positive. The first step in the Newton-Raphson method is just the initial guess, just like the other methods. We have here point 1, which may have many coordinates, but don't forget, in our surface we have only 2 coordinates, but we may have many coordinates. In a real case, we have a multidimensional surface, and each point in the multidimensional surface has many coordinates. After generating point 1, we need now to solve the Hessian matrix, which means we need to find each matrix element inside this matrix and then to find its inverse, h minus 1. To find its inverse means that we need to multiply h by h minus 1, and this would be equal to the identity matrix. The identity matrix has only ones in the diagonal and only zeros outside the diagonal. After having found the inverse of the Hessian matrix, we can now calculate the next coordinates. We are calling here q new. So the new coordinates are equal to the old coordinates minus a correction term. This correction term is just the result of the multiplication of the inverted Hessian matrix and the old gradient. This term we know already, this is the gradient. Then we keep repeating the steps above until the root mean square gradient is acceptably low. If we have just 2 coordinates here, it's possible to find the minimum in just one step. The Hessian matrix is used to predict vibrational frequencies. The Newton-Raphson method is computationally demanding, since we have to solve many matrix elements and we have to find the inverse of this matrix, which is also a lot of work. So it takes a lot of time, but it's very efficient close to the minimum. Here we see an example of the use of Newton-Raphson method to find the minimum of this function. And we can adopt the 0.99 as initial guess. We can just look at this function and we know already that the minimum of this function is located at 0 and 0. So when you put 0 in x and 0 in y, we would have the function will be 0. This is the minimum value that this function can assume. So let's apply this equation. The new coordinates are equal to the old coordinates minus the inverse of the Hessian matrix multiplied by the gradient at this point. So first let's find the gradient at 9, 9. The gradient is defined as the partial derivative of the function with respect to the coordinates. The first part is the x component of this vector. The second part is the y component. Deriving this function with respect to x and y, we get these numbers. But we need to find the gradient at point 9, 9. So we just have to put here x equal to 9 and y equal to 9 in this expression. And we find the coordinates of the gradient vector. The gradient vector is given by 18, 36. Now we have to find the Hessian matrix and invert it. For the first matrix element, we need to derive 2 times the function with respect to the coordinate x, to the first coordinate. So deriving this expression once more, we get 2. And this matrix element would be the second derivative of the function with respect to the variable y. So the students can try to find all the 4 matrix elements of the Hessian matrix. To invert this matrix, we need to multiply this matrix by another matrix, A, B, C, D, and equal to the identity matrix, 1, 0, 0, 1, so that we can find who is A, B, C, and D. By doing this, we find the inverse of this matrix, which is shown here. Finally, we use the main equation, and you see that the new coordinates are equal to the old coordinates, 9, 9, is our initial guess, minus the inverted Hessian multiplied by the gradient at that point. This is where the minimum is located. Now let's use the tinker to minimize the geometry of a cluster of 10 water molecules. Let's use the module Newton. First, let's draw the molecules using, for instance, Avogadro, but it's possible to use any other program like VMD or PyMol or HyperCam. Second, we save the cluster as PDB. When you're drawing this cluster, try to make a round cluster. At a certain point, you may need to rotate the whole cluster to add more water molecules on the sides, so that you have a ball, you have a 3D distribution of water. And we use the module of Tinker called PDB XYZ. We need to execute this module to convert the PDB file. We need to convert the PDB file generated in step 2 to a Tinker XYZ format. And we can choose the force field we want. For instance, let's choose the MMFF94. Then we open the Tinker XYZ file with VI in the Linux, or if you are using Windows, you can use TextPad or Notepad or even WordPad just to edit. For this force field, the oxygen of water and hydrogen of water are atom types 177 and 106. So we just need to substitute the zeros shown in this column, which should be the atom types, by the correct atom types. First atom is an oxygen, and the atom type here, instead of 0, should be 177. Second atom is a hydrogen, instead of 0, here should be 106. This is the file you get when you use this module PDB XYZ to generate the XYZ format of Tinker. We have atom names and XYZ coordinates, atom types in this column, and the next columns are just connectivities. For instance, atom 1, which is an oxygen, is bound to atoms 2 and 3. If you go to atom 2, is a hydrogen, atom 2 is bound to atom 1. So we have to check this connectivity to see if there is no problem, and the atom types we need to correct. So here instead of 0, 0, we put the correct atom types. We are using atom types, and the program uses atom types and determines the classes. The class would be 70 and 31. And just remember, the parameters are determined for classes and not for types. The program makes this automatically. 5. Check if atom types and classes were correctly assigned. In our case, atom types. This column should have the atom types 177, 106, as well as topology. The topology is shown here, the connectivities. Which atom is bound to which atom. Finally, we can run the module Newton. After running the Newton module, the cluster will be optimized until the gradient is as small as the threshold value you just gave. The standard value was 0.01 for this gradient. And then you take the output file, which would be XYZ underline 2, and you transform in PDP using this module XYZ PDP of the Tinker, so that you can take the output of Newton and transform to a PDB file. This PDB file may come with the underline 2 in the end of the file, so you just can remove this underline 2 and put just .pdb, and then you can open the generated output with VMD, PyMol, Avogadro, or any other visualization program. If we know how to calculate the potential energy of a system, it's also possible to make conformational analysis, where we can rotate around certain single bonds, as shown here. It's supposed to rotate, and for each rotation we make a geometry optimization. Here we have 4 different torsion angles. Here we may have different angles, theta 1, theta 2, 3, and 4. And in each case, we get the final energy of the optimized molecule. For instance, conformation 1 was done by using theta 1 of 180, theta 2 180, theta 3 of 180 degrees, and theta 4 of 0 degrees. And when we optimize the geometry, beginning with these parameters, we get this energy. So this is the input parameters, the input angles, and we have one output of the energy. We keep generating many different conformations with different input angles in order to sample the potential energy surface of this molecule. We keep doing this many times, and in the end we have, for different conformations of the angles, we would have different energies. After this conformation analysis, we can find the most stable conformers. In this case here, the most stable is conformer 3. Usually torsion angles involving heavier atoms are analyzed, no hydrogen, but in fact we only consider the heavier atoms like carbon, nitrogen, oxygen.